Hey everyone, and welcome to this video on the worked answers for the questions of lecture 8, and this is the first set of questions for the D block elements, which was questions 1, 2, 4 and 5. So question 1, we're looking at the electronic configuration of some D block atoms and ions. So if you remember, when we were looking at the electronic configuration of just the metals on their own, they usually fill in the order 4s2 and then the 3d, 4s orbitals and then the 3d orbitals. But there are a couple of exceptions, namely chromium and copper, and we'll actually see an example of those as we go through. You remember ions, they remove electrons in slightly a different way. And I'll highlight that first. So the first step was when we're working out the electronic configuration of an ion, is to write the configuration as though it was a metal. Then we have to move all of the the 4 s electrons into the 3d orbitals if there's room for them. So for some examples we saw in the book, like iron, there in the metallic state it's 4s s2 3d6. When we're working out for an ion, we can move those two 4s electrons into the 3d orbital because there's room. It makes 3d8, and then just take away what's necessary to get the ion you're looking for. Yes, cool. So with that in mind, let's go through these. So the first one we've got is vanadium 3+. Now I'll also put the noble gas configuration at the beginning as well. So the top row are the transition metals. The inner electrons have the noble gas configuration of argon, and then vanadium usually has a 3d3 4s2. So then, exactly as we said here, we put the 4s electrons into the 3d orbital, so we'll end up with 3d5, and then remove 3 electrons because it's 3+, the 3 oxidation state, and we're ending up with 3d2. B is just metallic ion, so I actually said about this one earlier. So metallic ion is a first row transition metal, so its inner electrons have the argon configuration. Then we have 3d6 4s2. So this is not an exception, it just follows exactly how we'd expect. The 4s orbital is filled before the 3d orbital. Chromium is one of the exceptions though. So chromium, again, we're just looking at the metal here. First row transition metal, so this has the inner electron configuration of argon. Then, however, it has 3d5 4s1. And the reason for this is that half-filled and filled d orbitals are much more stable. So instead of going 4s2 3d4 and leaving it with 4 electrons in the 3d orbital, we put that second one from the 4s orbital into the 3d orbital, so it's half filled. The same happens with copper, so that's 3d10 4s1, and that's because then it has a completely filled 3d orbital, which adds to its stability. The next one, D, is for silver. Now this is actually the second row of the transition metal, so this has a different inner electron configuration, this time that of krypton. And then exactly the same when we're working out the electronic configuration. This time we don't put them from the 4s to the 3d, we put them from the 5s to the 4d, if there's space, which there actually isn't in this case. So I'll write it out what it's like in this metallic form first. Is a 4d10 5s1. So this is directly below copper in the transition metal. So copper has a 3d10 4s1, as we were just saying. Silver has 4d10 5s1 because it's right below it. So usually when we're working out the ion, we do this next step, put all the s electrons into the d orbitals if there's space. There's not actually any space this time. So, and then we just take what's necessary. So we'll remove this electron here, make that a 0. So then silver 1+ is just a 4d10 electron configuration. So it's still got a completely filled d orbital. The next one is a bit interesting. So metallic ion, which we looked at in part B, but this time in complex. Now, one of the things that we talked about is how that when transition metal forms a compound, the d repulsions are minimized. So this time it's actually a lot more stable for all of the electrons to be in d orbitals than in the 4s orbital. Like, the only reason they like to go in the 4s orbital is to avoid these d orbital, like dd repulsions. Those repulsions are minimized now that the ion is in a compound. So this time it's still got the argon inner electron configuration, but all of the electrons are in the d orbitals, so it's just 3d8, and there's nothing in the 4s electron orbital this time. Copper 2 plus, quite similar to the silver plus that we were talking about. It's just above it in the periodic table. So Ar, I'll do the full metallic configuration again to start with. So this one's 3d10 4s1. As I said before, we can't actually put the 4s electrons into the 3d because there's no space, but it doesn't matter. We just start taking away then from the 4s orbital first. So we take 2 electrons, so one from here and one from here, and this ends up going to the 3d9 configuration. Ruthenium 2 plus, again down the periodic table a bit, it's in the second row below iron. So this has an inner electron configuration of krypton. Then we work out the electron configuration exactly the same again. So this time it would be in the metal state 4d6 5s2, much like the iron metallic state, but again 4 and 5 rather than 3 and 4 in the metal state. And then this time there is room in the d orbitals, so we put all of the s electrons in the d orbitals. That gives us 4d8, and then take what's necessary to give the right charge. So take 2 electrons out and we get 4d6. Finally, we've got tungsten, which is a bit of a special case because it's right at the bottom. It's the third row of the transition metals. So this time it's got the xenon inner electron configuration. The other thing we have to take care of now is that the lanthanide series has begun. So there are actually f orbitals to think about. So here we put the 4f14. So the f orbitals are completely filled, and then there are just 2 electrons in the d orbitals. And you'll notice that this time we haven't actually got an s orbital to talk about, like the 6s orbital, and that's because that's filled even before the 4f orbital. So if you draw out that diagonal rule diagram, so you'll need the first 6 shells, so like 1s, 2s, 2p, 3s, and do the diagonal rule, you'll see that they're filled actually in the order of so the 4d and then the 5p, 6s. So 4f is the orbital that's filled just before the 5d. Question 2 is a much shorter answer. It's just asking us to explain why the +3 oxidation state becomes less stable with respect to the +2 oxidation state as we go along the first row of the transition metals. So on the right here, I've got a table again of the most common oxidation states of the first row of transition metals that I showed in the second video of the first lecture. And you'll see at the beginning, scandium to chromium, +3 is more stable. Then we've got these manganese iron cobalt region where +3 and +2 oxidation states are both equally common. And then towards the end of the periodic table, nickel, copper, zinc, +2 is the stable oxidation state. +3 is actually quite unstable, and these compounds will be really strong oxidizing agents because of it. So why is this? This is all to do with the third ionization energy. So to get to the +3 oxidation state, you need to remove 3 electrons. You need to ionize it 3 times. So that's why the third ionization energy is important. And if you look at this graph here, I've got the ionization energies for the first 3 ionizations. The third one, as I said, is what we're interested in, and you can see it increases quite dramatically from just under 2,500 to just over 4,000 kilojoules a mole. So it's a big increase as we go across the first row of the transition metals. And it's the simple reason that when we get over to nickel, copper and zinc, the third ionization energy is just too high. So it's much easier for them to be stable in the +2 oxidation state rather than the +3 oxidation state. So it's just simply the value of the third ionization energy. Question 4 has given us the formulas or formulae of 4 coordination compounds and wants us to name them. Now, we all know that my handwriting is rubbish. I can't write on the screen very well, and I can't write and talk at the same time. So I saved us all the pain of that, and the answers are here in blue already. But what I will do is go through 8 or 9 naming rules and then apply them to each one so we can see why the names are what they are. So rule number 1 is cation first, anion second. This applies for compounds in general, but it's especially helpful to remember for coordination compounds since they can be really long formula. They can have lots of bits of them. So let's take the examples A and B to look at that first. Here we've got the complex ion in the square brackets first and the other thing second. So in this case, the complex ion is the cation and the other thing is the anion. B is the other way around, which means that the other thing is the cation and the complex ion is negatively charged. That's the anion. Now this brings me nicely on to the second rule. What happens when the the complex is negatively charged and it's the anion? Then it gets the suffix -ate. So take nickel for example. If nickel is in a positively charged complex, it's called nickel. If it's in a negatively charged complex, it's called nickel-8. This isn't the case for all of the metals though, and that's rule 3, which is be aware of Latin. 4 of the metals, iron, gold, copper and silver, when they have this -ate suffix, they switch to their Latin names. So iron in a positively charged complex is called iron. Iron in a negatively charged complex is called ferrate. So remember, that's iron, copper, gold and silver. Do that. The final rule with respect to the metals is the oxidation state. So that comes directly after the metal in brackets as a Roman numeral. So II if it's 2+, III if it's 3. You can also get up to 5, so in which case V is in the brackets. The next couple of rules are on naming of the ligands. So rule 5, the first rule is alphabetize. So you'll see this isn't the case when we look at the formulae. So take the first one as example again. We've got nickel and then we've got the iodine and then the ammonia ligands. This is because when we write the formulae, the anionic ligands are written first. So I is I-, that's written first, and then the ammonias are neutral ligands, so they're written second. When we're actually naming it though, we don't care whether it's charged or not. They just get put in alphabetical order. There is a slight naming change though for the anionic ligands. That's rule 6, and that's if the ligand is negatively charged, or an anionic ligand, it gets an O suffix to its name in the similar way that the metal gets the 8. So chlorine or the chloride ligand is called chloro. The same with all the halogens, they're fluoro, bromo, because they are negatively charged ligands. Rule 7 concerns numbering. So that's, remember, if we've something we add to show how many of each ligand we've got. So if we've got 2 waters, it's di. If we've got 3 chlorines, it's tri, and then tetra, penta, hexa, things like that, just to show how many ligands we've got. And then rule 8 is what I've called the number rule. And this is where if there's already a number in the ligand itself, something like a bipyridine, then the number showing how many ligands there are changes. Instead of being di, it goes to bis. Instead of tri, it's tris. Instead of tetra, it's tetrakis. And that goes Greek then. So numbers and then numbers. And the final rule, which I'm not going to write down, is don't worry about the naming of ligands in the exam. I'll give you the tables in the textbooks so you know what the names of each ligands are. So let's go through each of these 4 quickly, relating them to the rules, and we'll see how their names are built up. So the first one, we've got the complex first, and that's the cation. So we've got nickel, and then put the ligands in alphabetical order. We've got the ammonia first, and there's 5 of them, so pentaamine, and then iodo, because that's a negatively charged ligand, nickel 2, because nickel's in the 2+2 oxidation state, and then nitrate at anion second. The second example, the other thing than the complex is the cation this time. So potassium first, and then the complex is second, so it's the anion, so it's going to end up with 8. We've got 2 of these water ligands, so diaqua, and 2 of these oxalate ligands. Now, oxalate is negatively charged as well, so we put oxalato. Remember, negative charged ligands get the O on the end, so it's diaqua, dioxalato, cobaltate 3. Example C, or question C, part C, involves this triazaheptane ligand. Now you might be wondering, why is this name here? That doesn't look at all like dian. Shortening, and that's because this is from like the modern, very accurate IUPAC naming, whereas the old one comes from its old name, which was diethylene triamine. So yeah, you could also call this diethylene triamine instead of the triazaheptane. I wouldn't be picky. And because it has this di or tri at the beginning, depending on what you want to call the ligand, there are 2 of them. We call it bis, because remember, instead of di, if it's already got a number in the ligand, we go for bis. So it's bis 147 triazaheptane, iron 2 sulfate, because the sulfate is then the anion. Finally, we've got this sodium with a gold complex. So sodium's the cation because it's written first, sodium. And then we've got this gold complex, anion. So we put the ligands in alphabetical order, so bromine first and then chlorine. They're both negatively charged, so they've got the O on the end, and there's 2 of each of them. So it's dibromo, dichloro, orate. Because remember, when gold is negatively charged, it goes to its Latin name. So orate and 3, because it's gold in the +3 oxidation state. Finally, question 5 is the exact opposite of question 4. This time we're given the names of coordination compounds and we need to work out the formula. So I won't give rules this time, we've had them last time. We'll just apply what we know to the names and work out the formula. So this first one, you can see it's just one big long name, no spaces or anything. There's no cation or anion. That's because it's a neutral complex. So this whole coordination compound is the complex. So everything's going to be within the square brackets. So let's open up the square brackets. The metal always goes first, so chuck gold in there. And then we can put in the ligands. So chloro is Cl. And this diethyl sulfide, this one isn't actually in the book, but it's a good time to illustrate, the difference between methyl and ethyl. So methyl group is just CH3, and this is shortened to Me. An ethyl group is C2H5. So this is just a slightly longer carbon chain, and this ethyl is shortened to ET. So in the book, you've got dimethyl sulfide, and you'll see that's SME2. This time we've got ethyl, and the naming changes in a similar way, so it's just SET2. All in brackets to show that this ligand is this one sort of compound. And then we can just close it. That is the whole coordination compound. The next one is tetraethyl ammonium tetrabromoferrate. This has got cation, anion. So let's start with this cation. It's a bit of a more peculiar one that I don't think we've come across in the lectures. Tetraethyl ammonium. So ammonium is the NH4 plus cation. Tetraethyl ammonium is similar, but instead of having hydrogen, we've got these C2H5 groups again. So we can write it instead of NH4 as NET4. And that's the cation, NET4 plus. And then the anion this time is the metal complex ion. So open up the brackets, is ferrate, which is iron. So let's put Fe first. Tetrabromo, so it's just 4 bromide ligands. So Br4. And that is that coordination compound. The next one, again, has no big spaces. It's not cation, anion. It's just one neutral complex. So everything's going to be within the square brackets this time. So let's open them up. It's a molybdenum complex, so Mo first. Both of the ligands are neutral, so we haven't got any preference of putting the anionic ligand first. So let's just put them in the order they are. There's the first ligand is bipyridine. That's shortened to BIPI. And we see this bis, which means there's 2 of them. And remember, it's bis rather than di because there's already like a number indicating a prefix in the ligand itself. The second ligand is carbonyl, which is CO, essentially carbon monoxide coordinating as a ligand. And this is also di, so there's two of those as well. And this time it's di rather than bis because there's no number prefix already as part of the ligand. And then we can close the square brackets. It's all neutral. That is the entire coordination compound. Finally, we've got this potassium hexanitrito cobaltate. Horrible word. And before we go into this one, I'm going to focus on the ligand, this nitrito one, because it's quite an interesting one. And it's good to know how to write it because it can change. So I'll draw it here. We've got nitrogen with two oxygens. Now this type of ligand is called ambidentate because it can either coordinate by the oxygen, so the oxygen being the donor atom, well this oxygen, why not? One of the oxygens being the donor atom, or the nitrogen being the donor atom. Now it can't act as a bidentate ligand. You can't get both of the oxygens or oxygen and nitrogen. What we're interested in is whether the oxygen or nitrogen is the donor atom, and that's the definition of ambidentate. So this is reflected in the naming and the formula as well. So if in the example we've got here, it's nitrito, this means that the oxygen is the donor atom, and we reflect that in the formula by putting ONO. And then we know, it's almost showing how the oxygen is the thing touching the metal, so we put the O first. And that's nitrito, as we got in this example. You can also get it where the nitrogen's the donor atom. And in that case, the ligand is called nitro, and the formula is NO2, highlighting the fact that the nitrogen is the donor atom this time. So be aware of that when you're writing out the formula. So we'll start with the cation as we usually do. Potassium this time is K. And then we've got our complex. So we'll open the square brackets. It's a cobaltate. So let's put in CO. And there's hexanitrito. So in the brackets, the ONO, remember, because it's in the nitrito, the oxygen is the donor atom. ONO. Hexa, there are 6 of them. And then close the brackets. Now, there is one other thing we need to do here, because this isn't perfectly right yet, and that's deal with the charges. So it's nitrito. So we know that this ONO is a minus. We've got 6 of them, so the ligands actually give like a -6 charge. Cobalt, we can see from the oxidation state at the end of the formula, or the name, is 3. Cobalt's only in the +3 oxidation state, a +3 cation, which means the overall charge on this complex ion is actually -3. Now potassium is group 1. When potassium's a cation, it's only K+. So to make the cation balance with our -3 anionic complex ion, we've actually got to have 3 potassiums. So make sure to check the magnitude of the charges to, so that the cation and anion always add up to give a neutral coordination compound. And then that's that. That's taking the names and making the formulae.